Hi, I'm Dr. Philip Carlson. I'm from Belhaven University in Jackson, Mississippi, and I'm going to make a series of videos covering the material that we would normally go through in our General Chemistry 1 class. Eventually we might make it to General Chemistry 2 videos as well, I hope so. I'm going to be going through what we would typically cover in a normal semester throughout all of these videos, so that way if you happen to miss a lecture or two, you can come and find the video, or if you just want to get some more detailed information or just hear the lectures again, this is kind of what that's for. Alternatively, you may have found these videos because you wanted to just learn about chemistry, and this will be a good way for you to do that too. Although without the direct problem working, it'll be much harder to actually learn chemistry, but you can at least hear the different topics and whatnot, so you can get a sense of the different concepts that are involved. I'm going to be using Chemistry, a Molecular Approach, as you can see there, by Nivaldo, and this is a 3rd edition textbook. It's a pretty decent one. It's newer from Pearson, and I think it's a 2014 textbook. It serves as a really great introduction in the standard way to chemistry itself. So let's start at Chapter 1. We're going to talk about matter, measurement, and problem solving, as you can see there. One of the interesting things about chemistry is that we get to study matter. Matter is anything that has mass and occupies space. So really, that's a lot of stuff. That's pretty much everything. Well, almost everything. We're going to study some things that don't have mass, like light as well, or photons, if you will. So we'll look at a bunch of different things along the way, and you'll get to see all the traditional concepts. To start off in Chapter 1 here, we're going to talk about the composition of matter. So atoms and molecules in the scientific method. We'll talk about units and some different things along the way. One of the unique things about molecules, or matter, if you will, matter is made up of molecules and atoms, is the fact that the structure of these molecules, the way the atoms are arranged together, determines the properties of the substance. So the properties of the matter that you're looking at is determined by the atoms and the molecules that make it up. So for instance, take carbon monoxide here and carbon dioxide. Notice they both have carbon and they both have oxygen in them. Carbon monoxide only has one oxygen, that's the mono on the oxide, and carbon dioxide has 2 oxygens, that's the di on the dioxide. And even though they're both made of oxygen and carbon, they both are a colorless, odorless gas. One can burn, the other one is incombustible. One binds to hemoglobin, and the other one does not. So that's one of the big things. We all probably know that you can get carbon monoxide detectors in your house. Carbon monoxide is a poisonous gas that actually could kill you if you intake too much of it. That's because it binds to the hemoglobin in your blood. So it takes the place of where oxygen would normally be at. That carbon dioxide inserts itself into the protein there, eventually robbing your body of oxygen and killing you. But carbon dioxide, on the other hand, doesn't do the same thing in the same way. It's true if you were in any room without oxygen, you would die. That includes if it was full of carbon dioxide, but not for the same reasons that carbon monoxide is poisonous. So 2 very different substances. Carbon dioxide you exhale, carbon monoxide, usually whenever you have incomplete combustion or some sort of combustion reaction, combustion is a fancy word for burning, you can have carbon monoxide that is produced. So very similar molecules, they're made up of carbon and oxygen, but different properties. And how can we make sense of the fact that they have different properties? Well, we're going to look at their structure. And their structure in some way is going to determine the properties of the different molecules. So I've been using these words, atoms, molecules, and I haven't been telling you too much about what they are. So what is an atom and what are molecules? And what exactly is chemistry, if that's what we're studying here? So atoms are submicroscopic particles. Submicroscopic. They're on the order of about an angstrom, which is a fancy unit of measurement, meaning 1 times 10 to the minus 10 meters. So that's a really, really, really small length, and that's why they're considered submicroscopic. So if you had a microscope, these atoms would be smaller than what your microscope could view, or at least an optical microscope. It turns out that atoms are the fundamental building blocks of matter. everything is made up of atoms. Okay? That includes water, gases, the wall in front of me, the computer screen, my desk, everything is made of atoms, and so chemistry is a huge subject that has something to say almost about everything, depending on how far you like to stretch your chemistry, if it goes as far as physics or not. That's a question for another day. If you take these atoms, which are distinct entities, these atoms that make up everyday matter, you're probably familiar with the periodic table of elements. Those are all the different types of atoms that you can have. If you take those atoms and you attach them together, you have what's called a molecule. So two or more atoms attached together, they're attached by a chemical bond or a bond of some type. And those bonds form in particular geometrical arrangements, which is something we'll get to talk about in the future here. And these bonds can have different strengths, and they come in different ways, and we can model them very accurately, and you can use quantum mechanics to study them, and that's something else we'll get to talk about in this class. And it's interesting that molecules, when just taking atoms and combining them together, gives you all the matter that is around, all the matter that exists, and so it comes in different shapes and sizes and patterns and types. And so anytime we talk of molecules, we're talking of multiple atoms being bonded together. So those two ideas and concepts are perhaps one of the most fundamental things about chemistry. Richard Feynman, the famous scientist, Nobel Prize winner, inventor of quantum electrodynamics, was once known to say, if you were to erase all ideas of modern learning, and this is just a quick quote off the top of my head here, what could you tell the future after all the knowledge has been wiped away that would be the most helpful in one sentence? And in essence, he said it comes down to the atomic hypothesis, so that everything is made of atoms, and these atoms repel one another when squished too close together, or attract one another in different circumstances. And it's this idea that things are made of atoms that would really help drive the knowledge of everything forward again if all the knowledge was somehow wiped out. It's that important of a concept. And of course, the idea of atoms or what makes up atoms wasn't fully understood. We didn't understand the electron until the end of the 1800s, and then what makes up the nucleus of an atom. And these are things that we'll get to talk about here soon. So with this idea of atoms and molecules together, we have chemistry. Chemistry then is the science which seeks to understand the behavior of matter by studying the behavior of atoms and molecules. So we're interested in matter and the reactions that it undergoes, and that is the study of chemistry. Now, the origin of the word chemistry is pretty interesting and not nearly as straightforward as something like biology. We'll probably discuss that again at another time. So the scientific approach to knowledge is something that's relatively new. You've probably heard of the scientific method. And this idea really has arisen out of several people's ideas that came before. So philosophers originally, way back in ancient Greece, tried to understand the universe just by reasoning and thinking about it, but not by doing experiments. And really it took the Enlightenment and a few other ideas, a few other philosophical ideas to try to arrive at what we understand as science today. So scientists in general are just trying to understand the universe through empirical knowledge that they have gained through observations and experiments, trying to understand nature or matter and how it interacts and how it is made up. So that's what we look at in chemistry in general. So how do we gather this knowledge if that's what we're trying to understand? We're trying to understand the universe by gaining knowledge. How do we get this knowledge? And we do that by observation. So there are two types of observations that you can make. There's qualitative observations and quantitative observations. So qualitative just tells you about the quality of something, and quantitative tells you about the quantity of something, if you want to think about it like that. Not exactly the most rigorous definition, but it'll suffice for now. So if something is quantitative, it means you're putting numbers to it. 27 grams of sugar, 240 milliliters of soda. Qualitative means you're describing its qualities. It's brown, it tastes sweet, there are bubbles in it, and those sort of things. Describing its qualities. or are you giving some numbers to it and making it quantitative? Those are the two ways you're going to describe the observations that you make. Now, once you make enough observations, you can form a hypothesis, which is sort of basically just a way to take all those observations that you made and try to make sense of all of them together. So this is like a tentative interpretation or explanation of all your observations. And so perhaps the sweet taste of soda pop is due to the presence of sugar, is your hypothesis. So a good hypothesis, of course, is one that can be tested, or you can do more observations to try to show if your hypothesis holds. And it can be proved wrong. It needs to have the ability to be proved wrong. Otherwise, you're making statements that science can't say anything about. So your hypothesis needs to be falsifiable so that someone can perform an experiment or make an observation to invalidate your hypothesis. As you're testing your hypothesis, you're going to come along and you're going to make some experiments. So you're going to test your hypothesis by doing experiments, which is a set of highly controlled procedures designed to test whether or not your idea, your hypothesis about nature is valid, whether it holds true in new circumstances, in essence. And so the experiment generates your observations, and these observations you will use to validate or invalidate your ideas and your hypotheses. So it's kind of a system that we have working here, known as the scientific method. So if your ideas hold, you can eventually form a scientific law. And this is a statement that summarizes all past observations and predicts future observations. So a law is considered a very good statement that summarizes many, many observations and is very helpful to predict future ones. Okay, so something like the law of conservation of mass, which says in a chemical reaction, matter is not created or destroyed. So the mass is conserved. And it's this law that allows you to predict future observations, or to sort of tell ahead of time what you're going to see, because you have a scientific law that explains the observations from many experiments. So unlike a state law, you can't violate a scientific law. So that's a very good way to approach science in general. If you know about something that is truly a scientific law, and you should note that there are some things called laws that aren't really scientific laws, they just have that name because they work in a particular region, or they work really well, but they don't work exactly specific all the time. So anyhow, you can't violate scientific laws. And this leads to a number of different helpful explanations when you're looking at different observations. It immediately gives you a place to look to try to test what's going on. So your hypothesis is this potential explanation for a single or for a small number of observations, and eventually you form a scientific theory, which is a general explanation of why things in nature are the way they are and behave the way they do. So this is like scientific models, and these theories really are pretty well tested by all of your different experiments, and they're sort of what we would call the pinnacle of scientific knowledge, or the point to which you're aiming to get in your explanation of what's happening. So these also can be validated or invalidated by experiment and observation, and sometimes they're useful in particular contexts, and so they don't immediately go away and get replaced by something else, and they're constantly being revised. The way science really happens at the professional level is kind of this rolling set of experiments to which scientists try to give explanation but never fully commit to something, and so they constantly are making observations and saying, well, it fit with this idea, or it seems consistent with that previous experiment, and so this is what we think is going on, until someone else does another experiment and shows that your hypothesis didn't explain their work, at which point you might check it or disagree or some other thing. So it's not really cut and dry, sort of like these definitions would lead you to think. So if we were to put it all into a diagram, it would look something along these lines. So you can see this diagram in the textbook, figure 1.2 on page 4, if you have that with you. And this diagram kind of shows you how you're going to go through the ideas. So you may have observations first. This leads to hypotheses. which eventually leads to a law, and then you do some more experiments and you test them, and eventually you might make it to a theory, and you do some more experiments and you revise your theory, and it's all kind of a loop where they're all sort of connected, always waiting for the next experiment to confirm or to invalidate whatever scientific theory that you're testing. So if you were to place it into a table, it might look something along these lines. Notice describing what happens is your observations, and your law. Your law is describing what happens, applies to all events. Explaining why things happen, and why here is kind of a sticky word because you can't ever explain why to the most fundamental level. But you can understand why by choosing a nice hypothesis that helps to explain why you're making particular observations, and eventually you can turn that into a theory, which helps explain why you're seeing the different things in general that you are, and arranged in this kind of hierarchy where a theory is what you're aiming for, a hypothesis is what you're starting with, a law is what you're ending with, an observation is what you're starting with, and you want to get yourself to a situation that applies to all events, or all events within the realm that you're interested in. So these would be laws and theories, and that's the ultimate spot that you're trying to reach. Okay, this brings us up to the end of section 2. So we're going to stop here for now, and I'll see you back in section 3 soon.